Our today's topic is Laplace transformation. This is a very important and a very useful tool in mathematics, but especially in engineering, we use it a lot. While dealing with differential equations, you will see that we are very comfortably able to solve differential equations using Laplace transforms. When you will have equations like for RLC circuit and all, which is mixed with differential part and the capacitance, this will be L di by dt and this will be C dV by dt. So you will have a mix of variables or a mix of functions when you will be dealing with certain types of real-time problems. Their Laplace transforms come as a very handy tool in solving problems, or to say in solving differential equations. So today we will see what Laplace transforms are. Let's say we have a function ft defined for all t. Then Laplace transform of ft. This is called the Laplace transform operator, capital L. So Laplace transform of ft, it is defined as 0 to infinity e to the power minus st ft dt. So Laplace transform of ft is 0 to infinity e to the power minus st ft dt. What is S? S is a constant which can be real or imaginary. And since the result will be a function of S, this is written as function of S. This is the usual notation. These are the usual notations that you will see in your book and that you will be using in your examinations. So this is Laplace operator, a function in t defined for all t. When we transform that function, it is defined how we transform that function like this: 0 to infinity e to the power minus st ft dt. That is a function of S, Fs. So we have applied Laplace operator to this function to convert it as a function of S. Similarly, if we apply the inverse Laplace operator, L inverse of f of S, what we will get? We will get ft. So this is Laplace operator, Laplace transform operator. This is inverse Laplace transform. This is Laplace transformation. This is Laplace inverse transformation. The next thing is, what are the sufficient conditions for the Laplace transform to exist? That is, what are the sufficient conditions for Laplace transform? What this 0 to infinity e to the power minus ft st ft dt to exist? There are two conditions. First is that ft should be continuous. The function should be continuous. It should not be discontinuous. Second is, for s greater than some other constant a, the limit of e to the power minus at ft when t tends to infinity should be a finite number. This should be finite. It should not be infinite. So if these two conditions are met, then Laplace transforms exist. These are the sufficient conditions. The next thing is we have certain elementary functions that come in our equations very frequently. So we must know the Laplace transforms of those elementary equations. When we will have complex functions, we will apply our Laplace operator and find out the solution. But for there are certain elementary, like in differentiation and integration, you had a list of certain elementary functions and you had learned about them, like the differentiation of sine 80 is a cos 80. So similarly, we have certain elementary functions, the Laplace transforms of which we should keep in mind. The very first is 1, Laplace transform of 1. Let's see what it is. It will be, from our definition, 0 to infinity e to the power minus st function of t, that is 1 dt. No issues with this? This will be equal to e to the power minus st by minus s. Limit is 0 to infinity. When we apply infinity, this will be 1 by e to the power s infinity, that is 0, minus 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 plus 0. So this will be 1, then this will be 1 by s. Therefore, this is 1 by s. So Laplace transform of 1 is 1 by s. Learn it by heart. Second, Laplace transform of t to the power n. Very simple. This is 0 to infinity e to the power minus st t to the power n dt. This is the Laplace transformation. This is how we find Laplace transformation. Let's put st equal to p. Then s dt is dp. So what we will get? And the limits will be when t tends to infinity, p tends to infinity, so no issues. 0 to infinity e to the power minus p into t. T is p by s. So this is p to the power n by s to the power n dt. Dt is dp by s. This is equal to, this is s to the power n plus 1. So we take it out, this is a constant, s equal to n plus 1, integral 0 to infinity e to the power minus p, then is p to the power n dp. If you remember beta gamma functions, this is gamma of n plus 1. So this is like this, gamma of n plus 1 by, this is basically the definition of gamma function. So those who are not familiar with beta gamma functions, you will have to go to the chapter on multiple integrals and see what are beta gamma functions. This is an integration. So gamma of n plus 1 is defined like this. Actually in your books you will see gamma n, and here you will have p to the power n minus 1. So putting n minus 1 equal to n, this is n plus 1. And we have a value that gamma n plus 1 is given by factorial n for all n greater than 0. So if n is greater than 0, this is equal to factorial n. This is the result. Now we have two typical cases in this, particular cases I would say. So we have two particular cases. First is Laplace transform of 1 by root t. It comes to gamma of 1 by 2 by s to the power half. This is given by root pi. These are standard values that you can find in your book. Root pi by root over s, that is root of pi by s. This is one value you should remember. You will very frequently you will find this particular function in your equations. Second is Laplace transform of root t. This comes to gamma of 3 by 2 by s to the power 3 by 2, and this is root pi by 2 s to the power 3 2. You should remember these two values, or if you are very interested you can go to gamma functions and find these things out, but for the time being what I advise is just learn this by heart. Our next Laplace transform is, we had seen 1 and 2, now this is 3. Laplace transform of e to the power at. What we will do, we will start with the basic definition, 0 to infinity, e to the power minus st into the function of t, that is e to the power at dt. This is 0 to infinity, e to the power minus, when we take this will be s minus a t dt. What is it? This is e to the power minus s minus a t by minus s minus a, 0 to infinity. So the first term infinity, this will be 0. Second term minus minus plus, this will be 1. So this is 1 by s minus a. So the answer is 1 by s minus a. So Laplace transform of e to the power at is 1 by s minus a. Our next function is sin at. Very frequently we get sin at and cos bt. So Laplace transform of sin at. I will do, this will be 0 to infinity, e to the power minus st sin at dt. This is the definition. Now we have integral of e to the power ax sin bx. This was e to the power ax by a square plus b square into a sin bx minus b cos bx. This is a standard integral. Here e to the power ax sin bx. So here a is minus s and b is a. So we will put it here. This will be equal to e to the power ax, that is this thing, e to the power minus st by a square plus b square. This square plus this square, that is s square plus a square. Then we have a sin bx. A is this, so minus sin at minus b. B is a. So a cos at. The limit is 0 to infinity. What we will get? When the limit will be infinity, this is 0. So everything gone. When the limit will be 0, in minus this becomes plus, this becomes 1. So this will be s square plus a square in the denominator, and here this is s sin 0, that is 0. plus a cos 0, that is 1. So this is a by s square plus a square. So to write it properly, this is a by s square plus a square. So we get the value of Laplace transformation of sin at. Similarly, we will get Laplace transform of cos at. Let's do it. The more you solve problems, the more you will be comfortable with the topic. So let's find out that also. It will take 2-3 minutes, but if you will do this with me, you will be mastering this. So Laplace transform of cos at, 0 to infinity e to the power minus st. What we will write? Cos at. We know that integral of e to the power ax cos bx dx, this is equal to e to the power ax by a square plus b square into a cos bx plus b sin bx. This is standard integral. So we'll apply it here. A is minus s here and b is a. So this will be equal to e to the power minus st, a square plus b square, that is s square plus a square. In the bracket we'll have a cos bx, that is minus s cos at, then plus b sin bx plus a sin at. The limit is 0 to infinity, as it was in the earlier case. When it's infinity, this will become 1 by infinity, so this will be 0 minus this term. So minus of this term will be here. What it will be? Minus minus plus, so this will be cos of 0 minus a into sine of 0 by s square plus a square. This is 0, this is 1. So what we get? S by s square plus a square. So Laplace transform of cos at is s by s square plus a square. So these are the elementary functions for which we need Laplace transformation on a regular basis. There are two more functions for which we require Laplace transformations very frequently in solving differential equations. They are sine hyperbolic at and cos hyperbolic at. That is Laplace transformation of hyperbolic function. So let's see Laplace transform of hyperbolic sine at. What is this? First of all, this is e to the power at minus e to the power minus at by 2. That you know. So let's start with this. This is 0 to infinity. E to the power minus st, let's take half out. So this will be e to the power at minus e to the power minus at dt. This is half. This is e to the power minus s minus a minus e to the power minus s plus a t dt. This will be half e to the power minus s minus a t by minus s minus a minus e to the power minus s plus a by s plus a minus minus plus. So this is the integral and the limits are 0 to infinity. When we put t equal to infinity, this will be 0, this will be 0. When we put t equal to 0, these two terms will be 1. So this is 1 by 1 and this is in minus, so this will be plus. That is s minus a, this will be minus 1 by s plus a. Okay, let's expand it. This will be twice of s square minus a square. This will be s plus a minus s plus a. So this is 2a, s cancels, 2a by 2. So this will be a by s square minus a square. So Laplace transform of sin hat is a by s square minus a square. Similarly, Laplace transform of cos hat is equal to s by s square minus a square. This I leave to the students. Revise the chapter, see these things from your textbook and do this by yourself. Laplace transform of cos hyperbolic at. Do it. Tomorrow we will see the properties of Laplace transforms and then we will solve many problems. So this is your task for today. Do it in your copy. We will see tomorrow.